Hi, my name is Isha Venturasi, and today I will be presenting about my polymer project titled Comparative Study on the Surface Morphology and the Structural Properties of Bio and Non-Bioplastic. This study focuses on comparing a biodegradable polymer, polylactic acid, or we call it as PLA, with a conventional pattern-based plastic, high-density polyethylene, or we call it as HDPE. Plastic production has increased rapidly since it first began on a large scale in 1930s. Most conventional plastics are petroleum-based and non-biodegradable, which has led to a serious environmental concern. One of the most widely used plastics is polyethylene, particularly HDPE, which contributes significantly to our plastic waste. As a response to this issue, biodegradable polymers such as PLA have been developed as a more sustainable alternative. However, understanding how this material degrades under environmental conditions is important before they can be widely adopted. The main objective of this study is to compare the molecular structure and surface morphology of a bio-based polymer and non-bio-based polymers, specifically PLA and HDPE. The comparison was carried out before and after hydrolytic and photooxidative degradations, and it was characterized by using FIR spectroscopy and optical surface imaging. Ini untuk UV. Apa satu? Biar.
Okey, Ishi sedang meletakkan dia.
Untuk UV degrade. Macam ni je. Jangan sentuh. For result and discussions, first we will discuss about the FIR result for polylactic acid or PLA. PLA mainly degrades through hydrolytic degradations because its polymer backbone contains ester bond, which are chemically unstable in the presence of water. When PLA absorbs water, water molecules penetrate the polymer structures and break this ester bond, causing chain scissions and the formations of shorter polymer chains. For the FIR spectra, PLA before degradation show characteristic peak at around 1747, 1450, 1181, and 1081, which correspond to the carbonyl group CH stretching, CCOC stretching, and CO stretching, respectively. This peak confirm the chemical structures of PLA. After hydrolytic and photooxidative degradations, a noticeable change appeared around 2396, which correspond to the hydroxyl OH groups. The broadening and increase of intensity of this peak indicates that the formations of hydroxyl N group due to the ester bond cleavage. This confirms that the hydrolysis has occurred between the PLA change. Additionally, a weak new peak appeared around 1579, which is associated with the formations of a new carbonyl-related structure. Although this peak is weak, its present only after degradation suggests that the early stage of structural modifications in PLA. At the same time, a reduction in intensity of the main carbonyl peak at 1747 and the COC band at 1181 is observed. These reductions further support that the occurrence of ester bond breakage and the formations of carbonyl and hydroxyl N group. Overall, the FAR result shows that the PLA undergoes chemical degradations under both hydrolytic and photooxidative constraints. In contrast, the FIR result for commercial grade HDPE shows a very minimal changes after the degradations. HDPE is a non-linear polymer with a high degree of crystallinity and lack of ester or any other hydrolytically unstable functional groups. Its FIR spectra are dominated by a strong peak at 2913 and 2846, which correspond to the asymmetric and symmetric stretching of methylene groups. Additional peak at 1463 and 721 indicates bending and rocking vibrations related to the crystalline polyethylene structure. After hydrolytic and photooxidative degradations, this characteristic peak remain almost unchanged, indicating that the polymer backbone of HDPE remain chemically stable. Weak band observed around 1738 and 1239 are attributed to the trace carbonyl or CO groups from processing additive or minor pre-existing oxidative rather than true degradations. Since HDPE does not contain chromophoric groups that absorb sunlight effectively, photooxidative degradations is very limited. As a result, the FIR analysis confirmed that HDPE is highly resistant to both hydrolytic and photooxidative degradations under the experimental conditions used. Next, the surface morphology result to support the FIR findings. Before degradations, PLA appear very smooth, uniform and homogeneous, with no visible cracks or defects. This indicates an intact polymer structure. After 45 days of photooxidative and hydrolytic degradations, significant surface change are observed. The PLA surface become rougher and uneven with visible features such as pit, wrinkles, and dark spots. This defect suggests that the degradations has occurred mainly at the surface due to the ester bond cleavage and chain scissions. The degraded PLA also appear more brittle, even though no major cracking is observed. Water penetrations into the polymer leads to swelling, increase the chain mobility and eventual surface rearrangements. These morphological changes are consistent with the FIR finding, which shows the chemical modifications and formations of new functional groups. In comparison, the surface morphology of HDPE shows a very little changes before and after degradations. Both degraded and undegraded HDPE samples remain a relatively smooth surface with only a minor surface imperfections. No severe cracking, pitting or fragmentations is observed even after 45 days of exposure. This strong resistance to degradations is attributed to the HDPE dense molecular packing, high crystallinity, and low permeability, which limits the penetrations of water and oxygen. As a result, degrading agents cannot easily access to the polymer change, preventing both chemical and physical degradations. The morphology results are in good agreement with the FIR findings, confirming that HDPE undergoes minimal structural and surface modifications under the same degradation conditions. In conclusion, PLA shows significant chemical and surface change after hydrolytic and photooxidative degradations. FIR analysis confirmed ester bond cleavage in PLA, while surface morphology analysis showed increased roughness and surface defect. In contrast, HDPE remained chemically and morphologically stable throughout the degradation process. Overall, the PLA demonstrates a higher potential for environmental degradability compared to HDPE. And that's all from me. Thank you.